Hello everyone and welcome to part 12 of a To Be Astronomer reacts to a geocentric movie. Now, the last time I said that I will skip this part, but actually they don't talk about the significance of humans in any meaningful way. They talk about physics again, so I believe we should still cover it. Alright, let's continue.
In our universe, we have two great theories. God, in some sense, has a left hand and a right hand. The theory of the big and the theory of the very small.
I mean, I get what he's trying to say with it, but really, physics, if you will, is divided in four parts, kind of. There is classical physics, so things are not either too small, moving too fast, or too massive. Then there's quantum physics, in which things are very small, but are not moving too fast or being massive, which is kind of self-explanatory because they are not too, too big. Then there's relativity, where things are either moving too far, moving very fast, or having extremely much mass, sometimes both, but are not small. This is relativity. And when things are moving extremely fast and are extremely small, this is then kind of the particle physics, quantum. Some would say quantum chromodynamics, some would say quantum field theory, somewhere in that advanced quantum theories. In there, that this is kind of the four fields of physics that you could more or less basically divide physics under, right? And some things fall into these categories, sometimes multiple. I'd very much argue that cosmology clearly falls into the relativity side of things. And for example, things like nuclear physics would fall somewhere actually on the edge of from classical to quantum, to advanced quantum physics, somewhere in that kind of area, right? Yeah. So you can put all the specialties somewhere in there. Certainly, our day-to-day things like thermodynamics, especially on normal scales, statistical physics, again on normal scales, and classical mechanics, all falls within classical physics, right? So yeah, continue. Let's continue.
The theory of the big is relativity. It gives us black holes and big bangs and things we can see with the naked eye in outer space. Then there's a quantum theory, the theory of the atom. Now, the juncture between the two.
I mean, the quantum theory goes way beyond the theory of an atom. Way beyond. I mean, atom physics, like atomic physics or molecular physics and nuclear physics, all had their kind of their invention, not solely due to, but also due to quantum physics. So they definitely play a role there. But to say that quantum physics has only things to do with the atom would be very, very, very wrong.
That's when all bets fail.
And it actually split the two giant sides of the relativity.
Kind of, I mean, failed. It's the problem is that on a very, very small scale, we have problems understanding gravity. There are experiments, or like thought experiments, that you can do where you can clearly see that quantum mechanics and relativity would disagree on the outcome, right? But we know that either is, for practical purposes, true, or like as close to nature as they can be for our measurements. But somewhere there needs to be a disconnect. Some people think this will be solved when we find, should we ever find, the graviton, right? There are other ideas that are more fundamental. I've heard people say that maybe it is, we will never be able to find it because our mathematics is not sufficient, right? I'd like to mention Kurt Gödel's incompleteness theorem that he proved, right? So where he can disturbingly, the Gödel's incompleteness theorem has two possible outcomes: either that we can prove things mathematically that aren't true, which is horrible, or that that there are some things that are true in mathematics that we can't prove, which is also horrible. Either of these could also be because at those very fundamental levels, right, like higher quantum mechanics and general relativity are both highly mathematical in their description. Maybe the incompleteness theorem limits, kind of puts a lid on the maximum that we can know. Although this is speculation. I'm very much not a mathematician, so this is only speculation. I just thought that it's interesting to mention it.
Relativity side for the large and the quantum side for the small, and we haven't been able to unify all these things back together again.
There is
That is
a
true.
crisis in cosmology.
Well, I mean, I wouldn't call it a crisis. Cosmology is doing pretty well for itself. The nice thing about people who do relativistics and people who do cosmology, they are theorists, and I have quite a quarrel with a lot of theorists. But the nice thing about cosmologists is they know where their problems are, but they don't blow these problems up, right? They don't say, oh my god, it's a huge problem. The thing is, they say, no, we don't know it yet, so let's just focus on something else, some things that we can actually think about, like black holes, for example, where observational data is getting better and better, so theorists have more and more things to build their hypotheses around, right? So that's really, really nice. And they say, well, we don't know, but that's okay for now, right? We have still other things to do, and we'll come to the gravity quantum thing when we have more data on that. That's the really nice thing about most of the cosmologists I've spoken with. They know that there's a problem, and they're not ignoring it. They're acknowledging it's there, but they also say that let's not waste our time on that. Let's do something that we can do and we know how to do. And that's a really kind of this aids progress in areas such as cosmology, right? I really like this approach. So yeah.
Quantum field theory says there's this vast amount of energy in the quantum vacuum. If you do a simple-minded application of that to general relativity, it tells you the universe should be accelerating an incredible number of orders of magnitude faster than it is.
Usually in science,
That is true. I believe I've mentioned the vacuum energy problem beforehand, right? But the problem is that he said when we apply him to special relativity, to relativity, but that's not as easy as he makes it out to be, right? There are very many different ways that people thought that they can implement this vacuum energy. I talked about it in a previous episode, right? But like the different ideas of how much it actually differs from reality, they are quite a range, right? But yes, we were quite off, yes. But that happens sometimes. But I talked about it in a previous episode. We need to get on.
Off by a factor of 2 or a factor of 10, we call that horrible. We say something's wrong with the theory. We're off by.
I mean, given the poor data sometimes within astronomy, right? Because we are only observing the light of a very distant galaxy, and it needs to pass in some cases through our atmosphere, it passes through interstellar dust, it passes through the interstellar radiation field, and so on and so on and so on. So really, in astronomy, like for basic kind of estimations, being off by a factor of 5 is not a big problem for most parts, right? Especially within cosmology, when the things that you're looking at are so extremely far away that the data you're getting is really not great. So being off by a factor of 5 within cosmology, you're still at the right order of magnitude, and oftentimes that's the only thing that people are really interested for, is the basic order of magnitude, right? I remember fondly when one of our professors that we had in the cosmology course that I did, he said, well, yeah, so you multiply it with pi, but really you can leave the pi out. It won't change the order of magnitude. And that's the only thing that we really want to talk about, right? Because the uncertainties of our data are actually higher than pi, so you can just, this factor of pi won't change all too much. That's essentially what we're trying to say in cosmology. Not all of them, of course. There are some measurements that work really well, but for some measurements, really, a factor of pi off is quite all right. So, for example, but certainly in all other parts of physics, when you're off by a factor of 5, there's something very wrong.
A factor of 10. However, in cosmology, we're off by a factor of 10 to the 120.
They, first of all, not quite. The more extreme applications were off by 10 to the 120 something. The kind of your average application is only under only off by like 10 to the 50th or something, which is a lot less. They are still off, of course, but again, we know that they're off. It's not like we're saying, oh my god, everything is wrong. It's just we know that the ideas we have of the small scale don't apply to the large scale yet. Like, we haven't quite figured it out.
That is one with 120 zeros after it.
I love the horrible layout of the zeros that they have here. Why not just write all of the zeros out? I can tell you why.
120.
Because they're extremely lazy. They probably only did that part, changed out the first zero, the one here with a zero, and just copied it. Very, very, very lazy. If I do that in a presentation, first of all, I wouldn't write the number out like that because we have scientific notation for a reason. If I did that, most professors would not enjoy that very much.
Zeros after it. This is the largest mismatch between theory and experiment in the history of science.
It's not necessarily a mismatch between theory and experiment. It's a mismatch between the theory that we apply to the extremely small and the theory that has come out of some observations, thus more or less experiments, for a very, very big, right? So, you know.
Recently, some theorists have proposed that the need for dark energy can be dispensed with if we dispense with the Copernican principle itself.
Source, please. Never heard of that. Also, no, it wouldn't.
There's an important point here, because if you then said, okay, let's stop here for a minute, and let's suppose dark energy doesn't exist. Now,
if dark energy wouldn't exist, how are all galaxies around us accelerating away from us? Like, apart from those that are really, really close, like Andromeda. Andromeda and the Milky Way are gravitationally interacting so much that on these, even though these are already extremely high scales, right? Like extremely large scales, for me at least, for my usual topic of discussion, that these effects right there are too small to really play much of a role, right? But on huge scales, right? Every galaxy, regardless in which direction we are looking at, every galaxy that is not gravitationally interacting with the Milky Way so much that we are actually moving towards each other, is moving away. And not only moving away, it is accelerating. Okay, now let's put the Earth in the middle. What does it change? Absolutely nothing. Absolutely nothing. So, whoever this gentleman is here, he's very wrong when he says that.
the raw data is correct. It's what we observe. But let's just change the model a bit. Let's say, okay, let's suppose for a minute that the universe is not homogeneous.
Or, to put it another way,
if the universe was not homogeneous, how come that when you just look at a perceived empty patch in the sky, and every time we've did that, right, it looked the same? How can you then say that it's not homogeneous? It looks the same in every direction. Well, that's, strictly speaking, is isotropic, right? That's the second thing. But if you say that it's not homogeneous for whatever reason, right, that still doesn't align with our observations. We have reason to believe that the universe is homogeneous. There doesn't seem to be, on very, 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 very large scales, a big, not homogenic thing, right? There's not an area where galaxies are becoming less and less, like less, not probable, but like that there isn't an area where the farther out you move away from the Earth, suddenly galaxies don't appear anymore. That just is not a thing. That doesn't line up with observation. The cosmologic principle saying that the universe as we know it is homogenic and isotropic, so it looks the same in every direction, and there is roughly the same amount of stuff, regardless of how far away you are, lines up with observations a lot. Full stop.
let's suppose the universe does not follow the Copernican principle after all.
Let's see if we can fit
The universe doesn't oh god, they have still not understood it. The universe doesn't follow any of our principles. We tried to explain the universe with our things, right? And the Copernican principle, I've mentioned it countless times, the Copernican principle just says there's no reason why we should assume Earth to be a special place when we're talking about our observations. Otherwise, even like, just, so you can think of it, otherwise all of our observations would in the end be rather meaningless, right? if we say, well, the Earth's a special place. So every time when we look at something, we need to draw a line between, okay, the rest of the universe behaves this way, but not Earth. That's very, 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 very much special pleading and completely unnecessary to the discussion. Why would you do that?
exactly the same data with no dark energy? And the answer is yes, you can.
If we
I have never heard that before. I'd like to see the source for that. And well, you could maybe fudge the universe in a way, like squeeze it in such a way that all of the mass that we all of the galaxies that we see accelerating away from us are accelerating away because in an area that we can't see yet there is so much mass that kind of everything, that the Earth would be in some center and everything is being pulled away from the Earth, right? You could do that, but for that you would need to give Earth a special place again, and B, you would need to explain away huge amounts of mass, like ridiculously large amounts of mass that are in kind of a bubble extremely far away from Earth. Why? Those are phenomenally huge assumptions. You just can't make, really. That's ridiculous. It's like I might as well say, well, we can never explain it because it's just God. Sure, you can invent something, but that's not what science does. You can't just say, well, it's some of this stuff, right? You can't just invent your magical, your Deus ex machina, if you will, to solve all of your problems. That's not how that works, really. But I'm over 15 minutes already. Thank you for watching. Do all of the YouTube things, and until part 13 already. Oh God.